Okay, everybody have their answers. Anybody still working?
Still working.
Okay. Okay, we good? Vince, you still working?
Just about done.
I'm turning lights off for you, okay? Go. Prepare yourselves. Number one, capital H lowercase is a heterozygous genotype. Point on the wall where agree is. Agrees on the wall there. Where's disagree? When I say go, I want you to tell me if you agree. When I say go, do you agree or disagree? Go. Remember, you need to be prepared to defend your answer. Capital H lowercase h is a heterozygous genotype.
They're all followers.
Jonas, why do you agree?
Because the other one is when they're two of the same one.
What's the other one called?
Heterozygous or something like that.
This is heterozygous.
They're homozygous.
And what's different?
The other one is two of the same.
Same what? So it's A.
Alleles.
Alleles. Does everybody agree?
Yeah.
Heterozygous means what kind of alleles?
Different.
Different. Two different alleles, right? Number two, agree or disagree. You only need one recessive allele to see the recessive phenotype. Before you go, remember, phenotype means what? Physical, trait, appearance, anything like that, okay? Agree or disagree, go. Lexi, need two recessive alleles to see the recessive phenotype. How do we express recessive alleles? How do we know if an allele is recessive? What do you see? Lowercase letters, right? Number three, agree or disagree. Homozygous means that your alleles are different. Lexi, do you still think you agree or disagree?
Agree.
Agree? Why? Explain your thinking.
Homo is like the same letter, so it's like two capitals.
Okay.
Is that wrong?
And each letter, what does each letter represent? When you're looking at a genotype, what's each letter going to represent?
Oh, never mind.
Changing your answers. Okay, why are you changing your answers?
Because it's the same thing.
Lucy, you want to explain?
Homo means the same and hetero means different.
Homo means same. Remember, homo has two O's, right? Why are y'all doing that? Easy now. So if it means homo has two O's and that's the same, should your alleles be different or the same?
Same.
Same. Everybody good with that?
Yeah.
So confident, homo, hetero? Wonderful. Sit. Do you all remember when we were talking about twins? And we talked about identical and fraternal twins, and we talked about some people absorb their twins. things like that. I found a video that's pretty cool, honestly. And I think you all will be kind of interested in it. Before we get to that, your learning target today, when given an example, and this will probably, I'm just going to be honest, this will probably span over 2 days instead of 1 day, because I am not going to rush you all through this. This can get really complicated really quick, especially when you're first starting. When given an example, students can distinguish the difference between sexual and asexual reproduction. Oh, that's wrong. Yeah, oops. We're at the beginning, part one. Unless you all want to relearn about all that.
I don't.
No, I don't either.
No.
I'm gonna get to the fun stuff. Fun's where's fun. Okay, try this again. Students can successfully use a Punnett square to explain the possible gene combinations of offspring given a genotype for a trait. Remember, genotype is what? Genetic. Genetic. What?
Alleles.
Something in genetic makeup.
Okay.
Genotype is your genetic makeup, okay?
I said.
When we see genotype, what do we see? If I give you a genotype, what am I going to give you? Letters, right? Okay.
While searching for a kidney donor, a Boston woman named Karen Keegan stumbled upon a mystery. When her 3 adult sons underwent genetic testing to determine whether they were a match for kidney donation, the test showed that 2 of them weren't actually her sons. Keegan knew she was her son's mother. She had conceived and given birth to them. Figuring there must have been an error, her doctors pursued further testing, only to uncover something even more confusing. She was her children's biological aunt. It turned out that Keegan had a second genome in some tissues and organs. In other words, some of her cells had a completely different set of genes from the others. This second set of genes belonged to her twin sister, who had never been born. This condition, where an individual has 2 genomes present in the tissues of their body, is called chimerism. The name comes from Greek mythology, where a chimera is an amalgam of 3 different animals. Individuals with chimerism might have 2-toned skin or hair, or different colored eyes, but most are believed to have no visible signs of the condition. Chimerism can come from a twin in utero, from a tissue or organ transplant, or happen between a fetus and a pregnant woman. So how exactly does it happen? In one of the most common forms, a mother and fetus swap cells in the flow of nutrients across the placenta. The mother can inherit fetal stem cells, undifferentiated cells that are able to develop into any specialized cell. The fetal cells initially go undetected because the mother's immune system is suppressed during pregnancy. But in some cases, cells with the fetus's DNA persist in the mother's body for years or even decades without being destroyed by her immune system. In one case, a mother's liver was failing, but suddenly started to regenerate itself. Her doctors biopsied her liver and found DNA in the regenerative.
Oopsies. So. There.
Some might have acquired her second genome before she was born. Very early in her own mother's pregnancy with her, Keegan had a fraternal twin. Keegan's embryo absorbed some fetal stem cells from her twin's embryo, which did not develop to term. By the time Keegan's fetus developed an immune system, it had many cells with each genome, and the immune system recognized both genomes as her body's own, so it didn't attack.
So
or
she
destroy the
essentially
cells
has
with the second
her
genome.
DNA and her
We
twin's
don't know
DNA.
how much of her body was composed of cells with this second genome. That can vary from one organ to another, and even between tissues within an organ. Some might have no cells at all with the second genome, while others might have many. At least some of the egg-producing tissue in her ovaries must have carried the second genome. Each time she conceived, there would be no way to predict which genome would be involved, which is how 2 of her children ended up with the genes of a woman who had never been born. This can also happen to fathers. In 2014, when ancestry testing determined that a father was actually his baby's biological uncle, researchers discovered that 10% of the father's sperm carried a second genome from an embryonic twin. cases like this challenge our perception of genetics. Though there are very few documented cases of chimerism from an embryonic twin, we are all amalgams to some extent, carrying around the different genetic codes of our gut bacteria and even our mitochondria. And given that 1 in 8 individual births started out as twin pregnancies, there could be many more people with 2 genomes and many more lessons to learn about the genes that make us who we are.
Okay, I'm gonna give you all a few minutes to think about this. Okay? If I'm asking what do you think, is there really a right or wrong answer? No, I just want to know your thinking. This video explains that you can share as much DNA with a stranger as you do your own sibling, parent, or any other family member. How does this change the way that you think about inheritance and your family connections? Now, if I'm giving you time to think, should you be talking? Should you be making hand signals to your neighbor? No, I will give you time to talk, but right now I just want you to think. Okay? When you have your answer, I want you to put your head down. How does what you just saw change the way that you think about inheritance and your own family connections? Okay, hands up. I want you all, so we're going to take that hand up parent. I want you all to find one partner. Let's see. We're going to say that went to a different elementary school as you. Okay? What is the first thing you're going to do when you greet your partner?
Shake hands.
Shake hands and introduce yourself. Then what are you going to do? Discuss your answers. Then what are you going to do? We already answered the question. What are you going to do if you answer the question?
Shake their hand.
Praise them.
Yeah.
You say, yeah, that's a really cool answer, or I agree with you, or hey, I never really thought about it that way. And then you do what? Say goodbye. Go back to your seats. When you get back to your seat, I do need you to open your notebooks. Okay? Go.
Wing of the same. Wing of the same.
Lucy, I'll talk to you.
So I said no because you have no blood for strangers. You have blood for
That's kind of my more than like, what happens if there's stuff on your ad and they get fear and they trace your things. Everybody got their notebooks out? Anybody hear any answers that they thought were really cool, really different that they want to share? Or do anybody want to share their own? Vince?
I said no because like you don't have any blood with a stranger, so it's a very low chance. But like you share blood with like your siblings, your family, and all that.
So it didn't really alter your mind any?
No.
Anybody have any questions about the video? Yeah, Lucy?
So my mom always says that if you're left-handed, it means that you had it when like 10 years when you is that true?
if you think about it, we'll say there's 16 people in this room. I think there's about 16 or 17. According to the evidence in that video, 2 of you had a twin that you absorbed in the womb. You just didn't know. Or did anybody actually have a twin that they absorbed and they didn't know? Okay, so statistically, 2 people in this room had a twin that they absorbed. So there is a possibility that 2 of you in this room actually have 2 sets of DNA in your body. Just kind of
I think this.
Yeah.
Something about it.
It's pretty cool.
Wait.
What? What?
I'll guess something about bipolar.
Does
everybody know
Anybody know what?
if you're
So you actually can do DNA testing, and they can determine some of that stuff through DNA testing. Kind of the same way you would to see if you're a carrier of cystic fibrosis or things like that. So yesterday in our bell work, when we talked about being a carrier of a recessive trait, you can actually get genetic testing on tests for stuff like that. Anybody else?
could it happen to like a female and then like a man that's a twin, like a different sex twins? Like if the woman, so there's 2 twins, one a boy, one a girl, like a boy with mans.
Yep. Because so you don't develop your reproduction system until later on in development. So really, when you're still an embryo in the womb and you haven't quite developed into a fetus yet, you don't have any reproductive systems. Now you still have that DNA in you, but you're not necessarily. Yeah. Anybody else have any questions? Okay, Punnett squares. I need you all to dig deep in your brain and find those brain cells, okay? We're gonna get them working. I know it's early. This can get really complicated really fast. I'm gonna try to go slow and take it step by step. If you have any questions though, please stop me so that we can explain it. Okay? Everybody cool with that? Now, if you know something, do you have to write it down? No. Should you write everything on this slide word for word? Should you sum it up and keep it short and sweet? Yes. Punnett square is one of your vocabulary terms, so do you really need to write down the definition of a Punnett square? No, because most of you ace that test, right?
Yeah.
And you all should know what a Punnett square is by now.
Yeah.
2 big things though. We make Punnett squares using the genotypes of 2 parents. Genotypes being your what?
Your
Letters, your genetic makeup. Those alleles that are represented by those letters. And we express the probability from our Punnett squares in percentages, typically. That makes sense? Short, sweet, and simple. And then obviously Punnett squares is a tool that we use to determine the probability of an offspring being born with a certain phenotype. Phenotype is your what?
your physical.
Physical appearance, physical traits. Everybody feel good about that? Nobody have any questions?
I gotta write it down.
These slides are also available on Google Classroom. I posted them this morning, so if you miss anything or you need to go back or lost, confused, anything of the sort, they are on Google Classroom for you all. Everybody good? You good? Okay, you don't have to write this part down. But what I am gonna write down is we're gonna set up an example kind of to use as a guide when it comes to front of the board. Maybe. Okay, when you are setting up a Punnett square, obviously a square is a what? What's the square?
4 sides are equal.
4 sides are equal, 4-sided box, right? I would suggest, I don't claim to be displeasing, I don't claim to be an art teacher, so just bear with me. Start with your box, okay? In this case, we'll have a father and a mother, right? Because can you use Punnett squares for asexual reproduction? No, why? number one, what is that genotype? Dominant, but what? What other word can we use to describe it? We've got two dominant alleles that are the same.
Yeah.
Homozygous.
Homozygous,
Is that correct?
homozygous dominant. So we would say this follows genotype is homozygous dominant, which means it's gonna have how many alleles?
Two.
And are they gonna be different or the same?
Same.
Same, if they're the same, but they're dominant, are we gonna capital lowercase letters? Capital letters, right? Mother's genotype is gonna be what?
Do we homozygous recessive?
Homozygous recessive, right? How do you know?
Lowercase?
Both lowercase. So they're the same and they're lowercase alleles. Everybody good with that?
Yeah.
We're good with that, right? We practiced this yesterday, so this should be capable. For your Punnett square, it doesn't matter if it's the mother or the father. Parent one's genotype is going to go on top of these boxes. Okay? So parent one one's genotype is going to go up here. That could be your mother, that could be your father, it doesn't matter. So we've got our father's genotype up here on these two boxes. If the father and parent one's up on the top, what's going to go on the side? Mother's. Okay, so father's genotype's up on the top, mother's genotype is going to be here on the side. Or parent two. Everybody get that? Okay. Each genotype has how many letters? Two. How many boxes do we have up here?
Two.
Up here, just up here.
Two.
How many do we have right here?
Two.
Each allele is going to get its own box. That makes sense? So one allele here, one allele here. This A gets these two, this A gets these two. What you are going to do is you're going to drag this A. This A owns these two boxes. It gets to come down and hop down in these two. So how many blue alleles, that's your father, right? Does each box have one?
Yeah.
Is that the same case for this side? Do all four of these possibilities have one allele from the father? This A gets to come across from these two boxes. And same here.
Just good.
Now, do all four squares have one allele from the mom and one allele from the dad?
Yeah.
How many alleles do you get from your mom and dad?
One.
One from each. Give me how many total?
Two.
Do you see that on this Punnett square? Times 7. Each box. How many boxes are there here? 4. How many quarters go in a dollar?
25. Oh.
4 quarters go into a dollar. Now, Bentley, each quarter is worth what?
25.
25. Each one of these boxes is going to be 25%. Because remember, we express our probability as percentages. That makes sense for everybody? Everybody gets that? What is the percent chance that this offspring is going to be born heterozygous?
50. Oh, 0.
Lily, why do you say 100? What percent is this for? 25. Is this genotype heterozygous?
Yeah.
Is this genotype heterozygous? 25 plus 25 is what?
50.
Is this heterozygous?
Yeah.
25 or 50 plus 25 is what? What's this make it? makes sense? Simple enough? Okay. This is when it's going to get a little more complicated. We have two parents, a father and a mother. What is our father's genotype going to be? Is that heterozygous or homozygous? Heterozygous. How do you know?
They're different.
Different. What's different?
Letters.
Alleles.
Oh, yeah.
The alleles are different. So father's genotype is gonna be what?
B,
Big B, little b. What's the mother's genotype?
little b. No. Little b, big.
Big B, little b. Look at the side box, okay? What trait is big B gonna represent? Is that your dominant or your recessive?
Dominant.
And little b is your?
Recessive.
What phenotype does big B code for? Brown eyes. Okay, so the brown eyes, is that gonna be your dominant trait?
Yeah.
What's the little b gonna be?
Blue eyes.
Blue eyes. That makes sense? We're setting up your Punnett squares. What's gonna go up here? Father's genotype. So it'll be a big B and a little b, right?
Yep.
What about here?
Mother.
Big B, little b. What am I gonna do with this B?
Bring out.
It comes down, right? Does it go down just one box or both boxes? Both boxes. What's happening here? Comes down. Both boxes are one. Everybody's good with that, right? What's going to happen here? Where's it gonna go?
Both boxes.
Across both boxes. What about this one?
Same thing.
Both boxes, right? Do we have at least one allele from each parent? What is my percent chance that this offspring is going to be born homozygous dominant for brown eyes? So if it's homozygous dominant, what's its genotype going to be? Somebody restrain. Jonas, go. Homozygous dominant, what will its genotype be? Two big B's. Vince,
What?
what's the percent chance that this offspring is going to be born homozygous dominant for brown eyes?
45?
Huh?
50? Wait, no.
Homozygous dominant. David, what's homozygous mean?
Say, 25.
25%, right? How do you know that?
There's one box that has both.
One box has both. Gracie. What's the percent chance that this offspring is going to be born heterozygous for brown eyes?
50%?
How do you know?
Because two boxes have the same.
Two boxes are heterozygous. Family.
45.
How do you know?
Because one box is that.
One box is homozygous recessive. What color eyes is this going to have? This genotype?
Blue.
Blue eyes, right? If you need to go back and check, these numbers should all add up to be 100%. Can you have anything more than 100%?
No.
No. If you do have more than 100%, you know that you have messed up somewhere along the way.
Wrong.
Now, what is the chance that this offspring is going to be born with brown eyes?
50. 75.
25.
Everybody close your eyes. If you think it's 25%, raise your hand. If you think it's 50%, raise your hand. If you think it's 75%, raise your hand. Hands down. Open your eyes. Gracie, why do you think it's going to be 75%?
Because, like, the big B and the B and the little B is going to be brown eyes, and the 25 is 57.
How many dominant alleles do you need to see the dominant phenotype?
Oh.
One. How many of these boxes have the dominant allele?
3.
3, which means what percent is going to have brown eyes?
75.
75%. Makes sense? Okay. I want you all, we're going to work through this one together. Okay? This is what your problems are going to look like whenever you all are practicing here in a few minutes. Okay? I want you to calculate the probability. We express probability as what? Percentage. Calculate the probability for offspring from 2 parent cats. One cat is homozygous dominant for a long tail, so big T, big T. Parent one is gonna be what?
Dominant. Big T, little T.
What's that other word? Homozygous dominant. Big T, big T. Parent two, what's its genotype gonna be?
Homozygous recessive.
Homozygous recessive. Capital T, what trait is it gonna represent?
Dominant.
Long
Long tail. What's the little T gonna represent? Short tail. Everybody's good with that, right? What's the first thing I'm gonna do? I hear, okay. We're gonna do this together, but you all are going to be my brain. I'm going to listen to you all, and you all are gonna tell me exactly what I need to do, start to finish. What's the first thing I need to do? One person at a time. Actually, everybody stand up. Once you tell me a step, you may sit down. What's the first thing I'm gonna do? Make square. Shane. Draw lines.
That.
Get specific.
Kind of looking cross line.
Cross line.
Like from the top to the bottom, and then diagonal.
Where at? From the top to the bottom. Go to the middle, side, middle, top to bottom. Okay, that's one step. Parker, look for the next step.
You do it side to side, center.
Side to side and center.
Well,
You all gotta get specific.
from one side of the box to the other side of the box in the center.
Draw one line from one side of the box to the other side of the box in the center. Like that.
Yes.
Vince, what do I do next?
Put parent one on top.
Okay. You said, did you not say put parent one on the top?
Wait, then don't you put like both these and like above each box, above top boxes?
Specific.
I got it.
I'll let you think. What specifically do I need to do next?
Oh, put the parent one a little alleles or whatever there.
Put the parent one alleles over here. How?
You put one above each one of the top boxes.
But what is that?
The dominant allele.
The dominant allele on top of the box, like this?
Yeah. You want each.
One on each box, so that was dominant?
Yeah.
Cool. Sit. Stop. Heart your waters. What you got? What am I doing next?
You gotta put pant two on the side.
Parent two's going here on the side?
Yeah.
Abby?
Like label the parent to a list underneath parent.
What of those do I label?
Lowercase.
Lowercase t's, do I put them on the side of the box? How do I put them? Right here?
Like one on top of each box.
One on each box, okay. Think I can do that. Let's see now what?
Then you need to take parent ones, but you can put a capital T in one of the boxes and
So what do I do with this T?
put it in the box if you want to.
On top?
In the middle of the top box.
Bring it down, right?
Yeah.
Bring it down. Do I bring it down to one box or two boxes? Two boxes. Bentley, what do I do next?
Bring the little keys down across to the.
Bring this one across?
Yeah, both boxes.
Okay. Gracie?
Then you'll bring like the big T like down two boxes.
Bring the big T on two boxes. Other Bentley, what am I gonna do next? Little T, does it come across both boxes? Is there anything else I need to do? Lily? Calculate the percentages. So, those of you that are standing, actually that almost works out great. Lily, I'll let you sit. what? If it's homozygous, it's gonna be what? Are they gonna be the same or different? Homozygous, would be the same, right? Homo has two O's. Recessive means what kind of letters? Big letters or little letters? Little letters. Do any of these boxes have two of the same little letters? No. So what's the percent chance it's gonna be homozygous recessive? If none of the boxes have that. 0. Aaron, what's the percent chance it's gonna be heterozygous? 100%. Lucy, what's heterozygous mean? Different. I'll come up with questions for you eventually. I'll let you get this next one. Okay, I want you all to try this one on your own. You are going to cross two parent horses and determine that the probability that the offspring will have a black coat. Cross two parent horses and determine the probability that the offspring will have a black coat. Big B is black, little b is chestnut. Yep, in your note. Should you talk? Nope, this is just you. Don't forget, if you want to retake your vocabulary test, your first 8 retakes, first 8 words, will live through Punnett score, I believe. That is due on the 22nd. That is Monday. So if you want to take the first vocabulary quiz, that is due on Monday. This seemed pretty easy for you all. Okay, and clear as mud. Who's still working? Is anybody still working? Wonderful. Parent 1, what's our genotype?
Lowercase b.
Scientific words. How do we describe this?
Recessive
These are
allele.
my phone.
What is it? Recessive, but what kind of recessive? Homozygous recessive, which means it's going to be little b, right?
Yeah.
Parent 2,
Heterozygous.
heterozygous, right? One big B, one little b. Everybody got that far, right? Yeah. Drop the box. What's going to go up on top?
Parent 1.
Parent 1, what's parent 1's genotype?
Lowercase b.
Homozygous.
Recessive.
Recessive. What's parent 2's genotype?
Heterozygous.
Heterozygous. Everybody get that far?
Yeah.
What's going to be here? What's happening?
You're
This
right
B's
now.
going where?
Down.
She's going down. This B's going where?
Down.
Down. either of these have a dominant allele? No. What color coat are these two gonna have? Chestnut. Make sense? Everybody feel confident enough to practice some of these on their own? Yeah. Wonderful. Margaret said no.
Well, let's do that.
That's Cameron.
Okay. Easy now, we're gonna take it, Jonas. You are going to individually do some code square practice. If I say individually, should you talk to your partner? No. If you have questions, who do you get to ask? Me. No. I want to see where you are at in terms of doing code squares. Okay? You all have about 15-ish minutes left of class to work on this. Now, I need y'all to listen. On this worksheet, you practice heterozygous, homozygous. You're going to practice genotypes and phenotypes. And you're practicing Punnett squares. So this worksheet puts together everything we talked about for the last week-ish or so. Okay? When you're done, where do you turn it in? The tray. Okay? I will check back in with you all about 3 minutes until the bell, and we'll see how many of you all are done at that point. Okay? If I have a large majority of you all that are not done, I will give you all time tomorrow to work on it. But if I have the majority of you all are done, only a few aren't, it'll be homework. Does that make sense? Do you all want me to put on y'all's playlist?
Yes.
You all want the lights on?
No.
Okay. This is third period, right?
Yeah.
Has a picture. Okay, real quick. What does it mean if something is a purebred? If I say that dog's a purebred German Shepherd, what do I mean? They're both German Shepherds. Is it mixed with anything?
No.
So purebred, when we're thinking about homozygous and heterozygous, purebred would be another name for what? Homozygous. So hybrid would be heterozygous, because it's a hybrid mix, give a hybrid dog, mixed breed, right? Makes sense? Wonderful. line needs to be. Big line, little line. Okay, real quick, how many of you all are going to need more time to work? Okay, when you all come in, this is what we'll work on developing work, okay? Keep
Well, that history, that,
Those of you that are in the Perfect Square Club, have fun.
I will.
Where are you?
Shut up, Billy.
I'm not asking.
I used to do it.
Where?
They do it to them.
Your science teacher.
You would know.
Do science things.
I would do it on that.
You do it.
Yeah, I did.
Hey,